see. View and full screen. Okay, now that doesn't look too good. Let me see if I turn the lamps on here. And that might be a little better. Still got a little bit of a shadow in there. The items that I put on here kind of focused on fixed charge elements as much as anything, so we'll go over that in a minute. But this is quiz on nomenclature. And which of the following always has a -1 charge? And I gave you A, B, C, D, silver, chloride, zinc, and sulfur. Well, the one that always has a +1 charge is, of course, the silver. This is always a minus charge. Zinc's always a +2 charge. Now, sulfur can have multiple charges, but by itself on the periodic table, it has a 2- charge. Now, just to review that is always helpful. That would be a choice. Your fixed charge elements, just to group 1, group 2, and group 7 are fixed charge elements. All of those in this column are +1. Unless I tell you different. Like hydrogen can be a -1 under certain circumstances. The others are group 2, +2, and group 7. Don't forget that that's halogens. And these are all -1s. So when you're working with ionic compounds primarily, that's what these are fixed charge. If you get into molecular compounds, halogens will have a multiple series of charges based on the compound that they're in, or the ion at the end. We'll show you that in a minute. The other fixed charges depend on whether you can find silver and lanthanum. Let's see if I can find it. Tantalum, excuse me, not lanthanum, tantalum. Right here. You can start there and build it 2 blocks and then 3 blocks. This is circumstantial, as I pointed out last time. This is +1, +2, 2 blocks, +3, +3, +3. Well, you could guess all that to be +3, but tellurium has multiple charges, and boron, it has some weird charges in it in the structure. So these are the only ones that you should look at for right now. Now, coming through this direction, this is a +5, +4, and +3s. Now, this is consistent with being in that position. 3 blocks +3, 2 blocks +4, but it reads 1, 2, 3, 4, 5 in context on that. So the issue is try to learn what are fixed charges elements. If it's not a fixed charge, then it's, of course, there's multiple charges in the cationic structure if you kind of need that. Okay, so yeah, this is fixed, and we'll change that to match the question, B choice. This is fixed -1. This is fixed +2. This is variable, non-metal. Okay, number 2, real quickly. If calcium has an oxidation state of +2, and we hook that up with nitrogen -3, what would be the appropriate formula? Now, when you write your formulas, you have to remember that the sum of all the charges must equal 0, or the sum of all the charges must equal the net oxidation state. Now this, of course, is for the polyions. Okay, each element has its own oxidation state. Putting calcium together and nitrogen, you can switch the oxidation state numbers down to subscripts and would have an appropriate formula. Now the only way you can tell if that formula fits is conforming to these rules down here. Calcium, you have 3 plus 2 nitrogens, is 3 times minus 2 plus 2 times, well, plus 2, okay, minus 3's, and that would give you 6 minus 6, and that's 0. So that it's an appropriate collection of elements in the formula. One of the issues here that I just mentioned is the, let me see, that's C choice in that collection is net oxidation state. One young lady asked me today, CO3 minus. Okay, what's the oxidation of carbon? There's a double-edged sword here in the oxidation states. If the elements by itself, and we're trying to identify fixed charges as they are arranged on the periodic table, that's one thing. But when you include the element in a compound or polyion, especially in a non-metallic context like non-metal, the one side or the other may take on multiple charges, and the only way you can tell is calculate the charge that's on the oxidation state on that particular element. And in this case, you have carbon plus 3 oxidation states that must equal a minus 2 overall. And I indicated in last class or a couple of classes, the oxygen is always a minus 2 unless I tell you otherwise. Oxygen can have a minus 1 in compounds known as peroxides. However, I'll tell you that, and I'll alert you to the confusion to avoid confusion. So in substituting that idea, we have an equation and one unknown, and we can simply solve for carbon. 2 times 3 is a minus 6, transposed is 6 minus 2. Carbon in this formula, CO3, is carrying a plus 4 charge. Okay? As a matter of fact, carbon can carry a plus 2 plus 4. It can carry a minus 4. If it gains, it can either lose all of them or lose them in pairs. Okay? So we'll get to that when we get to bonding and talk more about why certain things are occurring as they do. But in polyions, you may be asked to calculate a oxidation state. Try for SO4 2 minus. See what that is. This is just for supplement. Salt 1 sulfur, 4 oxygens has to equal a minus 2. 4 times a minus 2 is equal to minus 2 plus your sulfur. And sulfur, solving this, is a plus 6 in that context. So when I say double-edged sword, they are taken into context from fixed charges like this, or if you have a formula, it's maybe something altogether different. Hydrogen's a plus 1, oxygen's a minus 2, and you can pretty well solve for any of the compounds that I will give you in the future. We'll cover this more in detail as we get deeper into the course. Any questions on that you need right now? Okay. Aluminum is a fixed charge element, and I gave you aluminum, sulfide 3. I wanted you to name that. And as we look at this, aluminum being a fixed charge is not required to have a Roman numeral. Now if we had, say, nickel sulfide of something like this, and it would be, say, matter of fact, nickel sulfide, that's the appropriate formula for that. Let me come back to that for a second. But this being fixed charge, you simply name aluminum sulfide. Even though it has a +3 oxidation state, it's not necessary to put in there a Roman numeral. Now nickel sulfide, let's come down here. Nickel sulfide, this has two notes you need to make. One, nickel in this particular case is a +2 and sulfur is a -2. But you don't see the subscripts down here. Remember what I said in ionic compounds. Metal plus a non-metal. The subscripts have to be reduced to the smallest whole number ratio. So if I switch the oxidation states and had this listed, it would be incorrect. If you can reduce them to a small whole number ratio, I can divide by 2, and the correct formula would be that. Okay? Everybody kind of comfortable with that? So, with one eye, keep that open. Okay? Okay. All of the following are ionic compounds except. Well, when you look at the periodic table, you want to find an ionic compound, as indicated earlier, is a metal element plus non-metal element except for H4 plus. When NH4 plus is the only cation that I will be giving you on the short notice. Now in the future, there are cations that enter into ionic structures, but that comes up in second semester, and we'll cover them. But for right now, the only non-metal cation that you'll have to worry about is ammonium. For example, Br minus, this might come up, ammonium bromide as a salt. Well, this is a +1, this is a -1, so the charges equal 0. Okay, now just re-emphasizing that. Okay, in the quiz, I gave you A, B, C, D, A, sodium bromide, mercury, oxide, calcium, nitrate, and N2H2 is hydrazine. Okay, of course, hydrogen is a non-metal. Even though it's on the left side of the periodic table in here, we still classify that as the non-metal. So we kind of bracket that off from everything else. Remember how I built a little staircase in here? Just to review this here. The elements that touch the staircase are called metalloids, like that. And basically, they can have functional cationic, metallic and non-metallic characters in some compounds. For the most part, for right now, keep it simple. Anything to the left of that staircase is a metallic metal. From the staircase across and back here. Transition metals, group 1 and 2, plus any of these in here. All those on the right side we'll classify as non-metallic for the short term, till I can get into some chemical bonding and show you how these metalloids function and so forth. Right now is not the appropriate time to do that. So in our collection, this is a non-ionic compound. Okay, all these are ionic compounds because they are composed of a metal and a non-metal. Okay, just some little rules you have to keep up with. Okay, and finally, now I kind of just gave the rule issue. Polyions will end in ATE or ITE. If they end in an ATE ending, okay, you drop the ATE ending and go ic acid, hydrochlorate, or something of that name, it becomes chloric acid. Or ITE ending, OUS acid. Some examples. ClO4 minus. Okay, that's perchlorate. Right there. Since we're -1, it will just need one hydrogen to neutralize that ion and would show up as HClO4. Now, as an ATE, we want perchloric acid. Would be the appropriate issue. And you can have the chlorate, and just to emphasize, ClO3 minus plus the hydrogen goes to HClO3 and just chloric acid. Now it's critical that you know the polyions. That's supposed to be a given kind of thing. NO2 minus versus NO3 minus. Both of them have negative charges on the nitrogen type, and so but this is nitrite and this is a nitrate, like that. Of course, then each one would need one hydrogen to neutralize the net charge, and we'd get an HNO2 or an HNO3. This is, of course, nitrous acid, and this one is nitric acid. So you kind of have to get comfortable with the ic endings and the OUS ending. Now, as I mentioned, the complexity of the nomenclature issues can get really into left field. And so by giving you that little flow sheet on that handout, I don't have a copy right on the tip of my finger here, but if you'll learn that, you can feel comfortable that my questions will remain in that chart. Now, some of the worksheets may have some kind of extraneous things if you run into it. Try to apply it to the handout. Somebody sent me, I can't remember, somebody sent me a note, and which, was it you that sent me a note about the chlorine fluoride? Somebody sent me a note about ClF3. Oh, come on. I think it was you, wasn't it? Yeah, ClF3, yeah, okay. Okay. ClF3. Well, you have two non-metals, and I've been preaching chlorides and halogens and -1 and all this. And when you put it in a compound, it becomes a little more complicated than what I have here. I've taught you to name the first one, followed by the number of elements in there. Well, that's true. It is a chlorine trifluoride, or something like that. And then some people will name this trifluoro, UORO. Sorry. Trifluorochloride. Well, this is what I've taught you up here. Both of them are correct. Okay, if you run into one, Google it. Wikipedia will have just all kinds of good stuff on a given compound that just write in the name as you think it is, and it'll pop up all kind of options and information on stuff, but both of these are correct. Okay, in some compounds, especially organic, you might have 15 or 20. They have systematic names, and they have common names, they have quasi-systematic names, and all this kind of stuff. So what I've tried to do is put it all on one page and a flow sheet for ionic compounds and fixed charges, volatile charges, and then acids and non-acids. And now remember, an acid to be an acid, and you want to keep this in the back of your head forever. For an acid to be an acid, it must be in water, the compound. It must be able to ionize and deliver hydrogens. And that's one theory. There are the three theories of acids and bases, and two of the three are compounds delivering hydrogens. These are classified as ionizable to deliver hydrogens. There is a theory called the Lewis theory that will take into account acids as being anything, and we'll get to that in appropriate time. But I wanted to address that. It was a good question you sent me, and I thought it would be worth sharing that with the class. Everybody, any questions on this?